So this is 4.1 notes. We're going to learn about angles. So a lot of this is kind of a review from geometry. So an angle is determined by rotating a ray, which is half a line, about its end point. The starting position of the ray is the initial side of the angle, and the position after the rotation is the terminal side. So you start at the initial side and end at the terminal side. In between the initial side and terminal side is your vertex. So where those two sides meet, that's your vertex. And in between there is the angle. The endpoint of a ray is the vertex of the angle, and this perception of an angle fits a coordinate system in which the origin is the vertex and the initial side coincides with the positive x-axis. Such an angle is in standard position as shown in figure 4.2. So initial side always starts at the x-axis here, and then it goes to the terminal side wherever that may be. Yeah. The terminal side can be wherever, just depending on how big the angle is. And then your vertex here is at the origin. So this is an angle in standard position. The first 15 slides of these notes are all kind of just vocab. So we don't really get into examples until the second half.
Oh yeah, is it gonna be the actual?
So positive angles are generated by counterclockwise rotations and negative angles by clockwise rotation. So if you start at the initial side here and go up, that would be a positive angle. If you go down, just think in the negative direction below the x-axis, that is a negative angle. So it's all based on the direction you go once you start at that initial side there. Angles are labeled with Greek letters such as alpha, beta, and theta, as well as uppercase letters such as A, B, and C. In figure 4.4, note that angles alpha and beta have the same initial and terminal sides. Such angles are coterminal. So in the first picture here, alpha is the one in the positive direction here, so it's going to be a positive angle. Beta is in the negative direction here. They have the same initial and same terminal side, so that makes them coterminal, even though they're going to have different measures, because one's positive, one's negative.
What do you mean they have the same initial terminal side?
This is the initial. Here, they start at the same spot, and they end at the same spot. That's the terminal. And then in the second picture here, they're also coterminal because they have the same initial, same terminal, but alpha just goes here. It's that little angle. Beta goes all the way around and then back to there. So again, these are coterminal angles. So they have the same initial, same terminal sides, but just different angle measures.
So ends up in the same spot.
Ends up in the same spot. The measure of an angle is determined by the amount of rotation from the initial side to its terminal side. One way to measure angles is in radians. The other way that we're probably mostly used to measuring angles is degrees. So we can go from radians to degrees, just two different measures of units of measure for an angle. So this type of measure is especially useful in calculus. To define a radian, you can use a central angle of a circle, one whose vertex is the center of the circle as shown here. So here our angle measure is this theta, and we would measure it in radians. Looking at this picture also, the length of this is our radius. That's what this R stands for. Theta is our angle. And the S here is the arc length. Arc length. Bless you. 1 radian is the measure of a central angle theta that intercepts an arc S equal in length to the radius r of the circle. Algebraically, this means that theta is equal to S over r. So this is one of our formulas that we have for 4.1. Theta is going to be our angle. Your angle theta has to be in radians. So whenever we use this formula, theta has to be in radians.
Like only beta, or you can use any angle or any kind of?
This formula is to find like whatever your angle is.
Okay.
So like theta is just one way they can call your angle. They could call it alpha, they could call it beta, just different names for it. But in this formula, you have to use radians when dealing with the angle.
But that gives you your radius, that formula?
Well, it depends. If it gives us our angle and our arc length, we could find the radius. If it gives us the arc length and the radius, we could find the angle measure by using this formula. So it would have to give you 2 of them, and you find the third. So the r is the radius, and then S is the arc length. And then theta has to be measured in radians. So 1 full rotation in radians around the circle is 2 pi. So it takes about 6.2 radians to get around the circle. So 2 pi is what? So 2 pi is radians. What would that be in degrees? If it's 1.
360.
Awesome. So 2 pi is 360. But 360 is just degrees, because 360 is how many degrees it takes to get around the circle. 6.2 is in radians, because that's 2 pi. 2 times pi would be 6.2. Yeah.
And how do you get that?
2 angles are coterminal when they have the same initial and same terminal side, so we did that in one of the first slides. For instance, the angles 0 and 2 pi are coterminal, as are the angles pi over 6 and 13 pi over 6. A given angle theta has infinitely many coterminal angles. For instance, theta is equal to pi over 6 is coterminal with anything that you add 2 pi to. So if our angle was pi over 6, coterminal, we would add 2 pi. And this n just stands for like how many times you go around the circle. So if n was 1, we would just be adding 2 pi. If we go around the circle twice, we would be adding 4 pi. So pi over 6 plus 4 pi would also be coterminal. So pi over 6 is about 30 degrees here. So this is our initial. That's our terminal. This is our angle here. That's pi over 6. That is coterminal. If I go around all the way once, so that's 2 pi going around once, and pi over 6 more, that's going to be coterminal with it also. I could go around twice, 1, 2, and pi over 6 more, and that's coterminal also. So you just add 2 pi, and you can get a coterminal angle. How would I add 2 pi to pi over 6?
You just like find the same denominator thing, how you add a regular fraction.
Awesome. I need the same denominator, so I'd multiply the top and the bottom by 6. So this becomes 12 pi over 6.
You don't touch the pi when you like.
Mm-mm.
No.
You're just multiplying the coefficients together. So pi plus 12 pi would be 13 pi over 6. So in order to add fractions, you need a common denominator. So for the positive angle, if we had theta is equal to 13 pi over 6, you would subtract 2 pi to find the coterminal angle. This is what we just did, but opposite, because we had pi over 6 and added 2 pi to it and got 13 pi over 6. So they're saying if they give you 13 pi over 6, you would subtract 2 pi from it. So if it gives you a positive angle, subtract 2 pi to find a coterminal angle. So here's another example. For a positive angle, 3 pi over 4, we subtract 2 pi to find another coterminal angle. So if I had 3 pi over 4 minus 2 pi, how can I subtract? Find a common denominator. So I would multiply the top and the bottom here by 4. So I would get 8 pi over 4. So 3 pi minus 8 pi is what? Negative 5 pi over 4. So negative 5 pi over 4 is a coterminal angle.
So how do we know when to subtract?
So if it gives us a negative angle, to find a positive coterminal angle, we would add 2 pi. So you can either add 2 pi or subtract 2 pi. Sometimes you can add 2 pi more than once, or subtract 2 pi more than once. So here, if we had negative 2 pi over 3 plus 2 pi, we would need a common denominator to add these two together. So I would multiply the top and the bottom by 3, so this would be 6 pi over 3. 2 pi plus 6 pi is 4 pi over 3. So this would be a positive coterminal angle with negative 2 pi over 3. So a second way to measure angles in the terms of degrees, noted by the little degree symbol. A measure of 1 degree is equivalent to a rotation of 1 over 360 of a complete revolution about the vertex. That's because there's 360 degrees in our circle. So to measure angles, it's convenient to mark degrees on the circumference of the circle as shown here. So it just shows the degrees written out here. So this angle here, theta, would be 45 degrees. So a full revolution counterclockwise corresponds to 360, a half revolution is 180, quarter is 90, and so on. Because 2 pi radians corresponds to 1 complete revolution, degrees and radians are related by the following equations. So 360 degrees is 2 pi radians, and 180 degrees is pi radians. Here we go. So to convert from degrees to radians, you multiply by pi over 180. To convert from radians to degrees, you multiply by 180 over pi. These are common degree measures. So 30 degrees is pi over 6, 45 degrees is pi over 4, and so on. I think the next slide, they have examples where we'll actually convert. Here we go. So converting from degrees to radians. So if I start with degrees, what do I have to multiply to get to radians? Pi over 180. So 135 degrees times pi over 180. So this would be 135 pi over 180, and then we just simplify. So do I have a number in common between 135 and 180? 5. So 135 divided by 5 is what? 27 pi. And 180 divided by 5? 56. Not 56. 36. And then you can also divide these again by 9. So 3 pi over 4. So 135 degrees is 3 pi over 4 radians.
Yeah, we have something in a fraction, right? We can't have a decimal.
Right. So you just multiply, and then from here, we're simplifying the fraction. So for the second one, if I have 540 degrees, how do I convert that to radians? Times pi over 180. So I get 540 pi over 180. To simplify, I can cross out the zeros, and then 54 and 18 have what in common? 3. So 54 divided by 3 is?
No, I mean, you divide by 18.
Divided by 18. Okay,
Equal 3.
that's right. So 3 pi. So you can divide both by 18. Okay, so hopefully you remember this from geometry. If we have two positive, keyword, they have to be positive, angles, alpha and beta are complementary, or complements of each other, when their sum is 90 degrees. So you're complementary if your sum is 90. Or if we were in radians, it would be pi over 2. Two positive angles are supplementary, or supplements of each other, when their sum is 180. So one way to tell the difference is, I think, like supplementary is like super, so that's the bigger one. The other one's just 90. So complementary is two angles that add up to 90, supplementary two angles that add up to 180. And both the angles have to be positive. So in example 4, if possible, find the complement and supplement of each angle. So if I had 72 degrees, I know that 72 plus an angle x is equal to 90. We'll get there.
Alright, sorry.
So just subtract 72 on both sides. So x is equal to 18 degrees. Another way that we could do this, so this is to find our complementary angle because they add up to 90. Another way is we can just take 90 and subtract 72, and that would give us 18.
You have to put the degree sign right or it's wrong. Like completely wrong.
Right, because how do I know if you're talking about radians or degrees if you don't put the degree
You
sign?
do know, it's just you have to put it.
Yeah. Now we can find the supplement. Two angles are supplementary if they add up to what? 180. So I would do 180 minus 72, which is 108. So 108 degrees is supplementary to 72 degrees. Any questions there? All right, for B, to find the complement, I would do 90 minus 148, which is negative something. Can I get a negative complementary angle? No, because they have to be positive, so there is no complement.
It has to be positive.
Yeah, that was the word that I circled twice on the last page.
Okay.
Positive. They have to be positive, so there is no complementary angle here. Now we can find the supplementary angle. So we would do 180 minus 148. What's 180 minus 148? 32 degrees.
So there's no second, I guess, supplementary.
Yeah, unless your angle is bigger than 180, then there wouldn't be a supplementary angle.
Do we have to show if it's over 90 degrees?
No, you could just say no complement. If you look at it and see that it's over 90,
You have like a negative angle.
right. So complements we know add up to 90, but what's 90 in radians?
Pi. No, half pi.
Pi over 2. And supplementary add up to 180. So what's 180 in radians? Pi. So we're doing the same thing. It would just be pi over 2 minus whatever angle it gives us.
You get 5 over 2 from like
Well, we could set up a proportion because we know that 360 is 2 pi. So if I want to find what 90 is, I could set up a proportion, cross multiply.
What was one?
Pi. So 90 is 1/4 of 360. So then 1/4 of 2 pi would be pi over 2. That's a common one that you should know. 90 is pi over 2. Or you could convert. You can multiply from degrees to radians.
No, see, that's what I do.
Like when you use that one, do you have to convert to anything, or you just use it?
Well, we can find the complement by, we know complementary add up to 90. What's 90 degrees in radians? So pi over 2 minus 2 pi over 5. What do I need in order to subtract fractions? Same denominator. So I'm going to multiply the top and the bottom here by 5. So I get 5 pi over 10. Subtract, and I have 3 pi. Well, this one actually, I have to multiply 2. So I have to multiply the top and bottom here by 2. So I have 4 pi over 10. Now I can subtract. So this would be pi over 10. Yeah, that's what I did.
So it was pi over 2.
Yeah, I made it 5 pi over 2. All right, to find our supplement, we know supplements add up to 180. So what's 180 in radians? So I would do pi minus 2 pi over 5. So here I'd have to multiply the top and the bottom by 5, make it 5 pi over 5, and then subtract. So this would be 3 pi over 5. That's my supplement.
And what is it?
3 pi over 5.
How do you know whether it's complementary or supplementary?
Complementary add up to what?
180. Oh, 90.
90. Supplementary add up to 180.
But isn't it just actually
But
for
if
both?
you're, yeah, so you're.
Okay, so then if we find the complement for D, complement add up to 90, what's 90 in radians? Pi over 2. So pi over 2 minus 4 pi over 5. Again, I need to find a common denominator, so I'm going to multiply my first fraction by 5. So I would get 5 pi over 10. I'm going to multiply the second one by 2. So I get 8 pi over 10. What's 5 pi minus 8 pi?
Negative 3 pi.
Can I get a negative? So there is no complement. Now to find the supplement. I know supplement adds up to 180, so what's 180 in radians?
I have a question.
Yes.
You have to put a degree sign for the fraction one answers.
Are radians in degrees? No.
No.
And you don't even have to write the word radian when talking about radians, because if you don't have a degree, it's implied that it's a radian. Okay, so pi minus 4 pi over 5. I'm multiply the top and bottom here by 5. So 5 pi minus 4 pi is pi over 5. And that's my supplement. So next we're going to find the linear and angular speed. So for a circle of radius r and central angle theta, intercepts an arc length s given by this formula. So this is our arc length formula. Arc length is s. So s is equal to r times theta, where theta has to be in radians. So this is actually the same slide on like slide 6 or something. We've seen this before. So for example 5, a circle has a radius of 4 inches, so our r is 4. Find the length of the arc intercepted by a central angle of 240 degrees. So our arc length formula is what? S is equal to r theta. So we're looking for S. We said our r is 4. What's our theta? 240 is in degrees. What does theta have to be in? Radians. So I have to convert 240 to radians. So what do I multiply to convert from degrees to radians? Pi over 80. So this would be 240 pi over 180. You can cancel out the zeros. 2 goes into both of these, so it would be 6 goes into both of them. So 4 pi over 3. So our theta is 4 pi over 3. So in my equation here, I have S is equal to 4 times 4 pi over 3. So S is equal to 16 pi over 3. So here we have the linear speed formula, so we could find the speed of how fast our particle is moving, so that would be here. So that is our arc length over time. What's our formula for arc length? S equals R times theta. So linear speed could also be measured in R times theta over time, because R times theta is the same thing as S. Yes. You also have your angular speed, which is how fast the angle changes, so that is theta over time. So your central angle divided by the time. So the second hand of a clock is 10.2 centimeters long, as shown in figure 4.11. Find the linear speed of the tip of this second hand. So our linear speed formula is what? R theta over time. So I have to figure out what my R is, what my theta is, and what my time is. What's our R? 10.2. So before we go on with this problem, whenever we have clock problems, so if I had a clock here, and if I was just looking at a quarter of my clock, so just this part, this would be 1/4 of my clock, or a quarter. How many degrees? 90 degrees, which would be how many radians? Pi over 2 radians. And how many seconds? Yeah, if the whole circle is 60 seconds, 15 seconds.
Wait, the whole clock is 1 second?
60. Okay, so next, if I had half, this would be 1/2.
It's 30 seconds?
It would be 180 degrees, which would be what in radians? Pi radians. And how many seconds? 30. Next, if I had 3/4. So 3/4 or 3/4. This would be 270 degrees. 3 pi over 2. And 45 seconds. And then lastly, if I had the full circle, so this would be full, 360 degrees, 2 pi radians, and how many seconds? 60 seconds.
We're only gonna use seconds? Or?
When dealing with a clock, yeah.
Are we gonna put the clock problem in?
Possibly. So here I'm trying to find the linear speed of a full rotation around the clock. So I'm going to use this one here. So what would my theta be? Theta has to be in radians, so 2 pi. and time is 60.
But how do you know it's too high? Is it like showing like cause the quarterly and the half, like?
I'll show you. But let's just say we have a full rotation here. So we're going to use this formula, r times theta over t. So r is 10.2, theta is 2 pi, and t is 60. And then we just put this into our calculator. What do you get?
So we can use the calculator for this part.
Yes. So you get 1.068. And then what, like, measure is this? What would our units be? Nothing in here is in degrees, right? We have radians. We have,
Whatever linear speed's supposed to be.
what's our length, what's our radius in? Centimeters. And then what's the 60? Seconds. So centimeters per second. So this would be our answer. So that's how fast our speed is.
Are we done?
Almost. You asked a question, so I'm going to answer it next.
Oh, okay.
So if this was a half rotation, so 10.2 would be our radius still. Theta would be what? If it's a half? Pi. And what would time be? 30. So if we had 10.2 times pi over 30, what do we get when we put that in the calculator?
Still says 1.0.
1.068 centimeters per second.
So you did that for all of them?
Yep. Does the second hand ever change its speed? No. That's why.
Okay.
So it's not like it's speeding up when it's just a fourth of the circle. It's just different proportions. So you could use either one.
So you could use any of the four?
Yep.
Then why was the point of showing this stuff if you could use any of the four?
Because it depends. If it wasn't a clock, it would be different. So the point of me showing you them is so you know